Good morning, good afternoon, good evening, wherever you may be in this part of the world, and welcome to another session of my presentations series, another interesting topic, and that is understanding the nameplate details of a medium voltage transformer or potential transformer. And basically, you can either use those names interchangeably. You can say a potential transformer or a voltage transformer. And this equipment is mostly installed on a medium voltage switchgear. Medium voltage switchgear in a PT compartment or auxiliary compartment. That's how they call it. So there's a dedicated compartment specifically for the mounting of the voltage transformer or the potential transformer. So anytime you go to the substation, ask for an auxiliary compartment, and you'll find where these voltage transformers are located. My good name is John Kweku Amotu, and I've been a professional electrical engineer for the past 31 years. I've been practicing in the United States for the past 31 years. If you like this my presentation and any other presentation that is shown on my YouTube, don't forget to subscribe. And if you like this one, select the like button, and don't forget to share this video. Also, you can go to this my YouTube channel, and there are tons and tons of presentation materials, learning materials that you can basically watch. And as a developing engineer, young engineer that wants to go into power systems, and manufacturer project engineers, other discipline engineers, road engineers, and mid-career engineers and experienced engineers, consulting engineers. These presentations that are shown on my YouTube will be very good for you. And matter of fact, mid-level engineers and experienced engineers, consulting engineers, this also can be a refresher for you. Now let's take a look at the functions of a potential or voltage transformer. Okay, so its function is to scale down the voltage from 34.5, 13.8 kV, 6.9 kV, 4.16 kV. And matter of fact, there are some switch gears that are at 2.3 or 4 kV to a secondary voltage of 115 volts. So its goal is basically to scale the voltage from a very high voltage, which will not be ideal and can be disastrous if we connect those high voltages to instrument voltmeters, watt-hour meters, and also protective relays. So that is why we scale it down to a usable, adaptable voltage of 115 volts. That is ideal for the voltmeter or protective relay or watt-hour meter. Okay, so now let's take it, and they are mostly, all the time connected in a shunt configuration or power connected. So this is a typical picture of how it looks in a switchgear. Okay, so now let's take a deep dive into the components of the voltmeter or the potential transformer. Okay, so this is the primary terminal, right? Okay, so this is where you apply 34.5 kV, 13.8 kV, 6.9 kV, 4.16 kV, 2.3 kV. So that high voltage comes to this terminal and energizes this primary winding. So this one is the high voltage winding, right? So there are two windings. The external one, the outer one, is the high voltage winding, and the inner one is the secondary winding or the low voltage winding. Okay, so for this one, this will be all the voltages from the high voltage side that can be applied. And on the low voltage side, you have 115 volts. Okay, so on the low voltage side, these are the wiring from the low voltage winding that is brought outside to the low voltage compartment box. It's a small box that is external or adjoined to or connected externally to this PT box over here. Okay, so out here is your 115 volts. That is what comes out of the secondary compartment over here. And you have the earthen screw over here. Next is the iron core, right? Okay, so the core over here is the one that carries the magnetic flux, right? So once you energize the primary side, right? The primary side basically induces a current that basically creates a current that creates a magnetic flux, right? So that magnetic flux flows through this part and induces voltage into the low voltage winding. Okay, so the magnetization branch is the one that carries the excitation current, right? So there are two branches for the excitation current. The X part and the R part. One pertains to the hysteresis and the other one pertains to eddy current losses. Okay. So this is a similar, the other one is a similar picture of the potential or the voltage transformer. Okay, so next is basically, another picture that shows you the secondary wiring. Remember, I told you that the secondary wiring basically it's a joining box that's connected to the PT, right? So these are the external wiring, the wiring that comes out of it, and to whatever integration that you want to integrate. That is the voltmeter, watt hour meter, and potential transformers, and protective rails. Okay. So remember that the secondary side is also fused, right, to protect the secondary side circuit. The primary side is fused, and this one is basically the fusing for the primary side. Okay, it's three of them, three fuses, one in each phase. Phase A, phase C, right? Okay, so these are called fingers. They are called fingers, based on how they look like. Okay, so in the switch here, you have the horizontal bars, right? A, B, C. Then you have the vertical bars, right? So these get bolted or connected to the vertical bars, right? So these fingers or the stubs that you see over here are the ones that get connected over here. Okay. So this is what energizes this PT, right, in each phase over here. Okay, then it goes through a fuse, right? Remember, you need fusing to protect the circuit. So A, B, C, right? Then there's a clip below that goes to, so that's the clip that you saw on the previous slide. It goes inside the PT and it gets connected to the high voltage winding. Next, let's talk about the different configurations that we can have for VT or potential transformer. The first one is open delta or residual winding. Okay, so as you can see over here, phase A, phase B, phase C. Okay, Okay, so as you can see over here, this is Y ground, right? The primary side is Y ground, right? As you can see over here, it's grounded. But the secondary side is open delta. Okay, so basically you have 3VO, which is VA plus VB plus VC, right? So they call it open delta configuration. Then you can have a YY configuration. That is what you see over here. So the primary side is connected in Y and the secondary side is connected in Y. The first thing that one of the things that you see is the name of the manufacturer, right? Okay, so you can see all the big players in the manufacturing of the VTs, right? Okay, so the VTs, the medium voltage plus VTs have a large umbrella, portfolio of manufacturers. So let's talk about a few of them. It's GE, ABB, Schneider, Alstom, Siemens, Powell, and many more, many industry players in that. So the next one is accuracy class, right? So the accuracy class is based on the ratio error N1, N2 is equal to V1 and V2, and the phase error between the primary and the secondary. Okay, so the phase error has to be within the setting. Then the standard that was used for the manufacturing, and the type and the model of the VT order. And then the primary voltage. So in this case, this will be 34.5 kV, right? 13.8 kV, 6.9 kV, 4.16 kV, 2.4 kV. Okay, so just to name all the different media voltage levels that we have. Then the secondary voltage, which can be 115 volts. Right. Next is the frequency, either 50 hertz or 60 hertz. Next is the voltage factor. Okay, so the voltage factor basically tells you how much over voltage operation, let's say during emergency conditions, if you want to exceed a over voltage condition, let's say 1.2, which is basically to 120%, or 1.9, which basically equals to 190% of the nominal voltage, how long you can operate in that condition without exceeding the thermal limits of the voltage transformer or the potential transformer. So as you can see, sometimes you see that 1.2 continuously can be done, and 1.9 they will say that maybe for 8-hour period. 8-hour period. Next is the accuracy power, right? Accuracy power will tell you how much VA of load, and that is the load of the voltmeter or the protective relay or watt-hour meter that you can connect to this voltage transformer. Next is the year of manufacture, right? Okay, and the maximum system voltage. So if you have a voltage level of 115 kV, right, the maximum you have is 132 kV, and if you have a nominal voltage of 230 kV, the maximum is 242 kV. Right? If you have a nominal voltage of 345 kV, the maximum is 362 kV, and so forth. Okay, then nominal system voltage is what I gave you all the nominal system voltage and the maximum system voltage. Then the power frequency withstand voltage. Okay, so that is the voltages that occur in the power systems that the voltage transformer or the potential transformer has to withstand, right? And there are certain conditions, certain phenomena that should occur in the power systems for a power frequency condition to experience an over voltage conditions. And the first one is load rejection. Next is fault recovery after fault clearing of a phase to earth fault. Next is ferroresonance condition. Ferroresonance condition basically occurs when you have an equipment that has inductance and capacitance elements, passive elements, and that is connected in series. It integrates to external passive elements, inductors and capacitors in the power system network. So you can have a capacitor bank in the power system network. You can have a reactor in the power system network. So these passive capacitive network elements integrate and basically can create resonating voltages. So that is what ferroresonance phenomenon is all about. Okay, so all these conditions can create over voltage conditions, and the VT has to withstand that. Okay, so for 115 kV, usually the power frequency withstand voltage should be about twice that. Right, so that is 230 kV. Next is the basic insulation level. That is the impulse withstand. Right. Okay, so that is one is due to switching And what do you mean by switching? That is when we are operating a circuit breaker in close proximity to the location of the switchgear that basically houses the potential transformer or the voltage transformer. And that switching conditions can create that over voltages, and the potential transformer or the voltage transformer has to withstand that. Also, you can have lightning strikes, right? That lightning strikes can basically induce very high currents, and also DC offsets that can, and based on the configuration, especially the Y grounded, can create paths for these lightning currents. And so the insulation system has to withstand that. Next is accuracy and burden, right? Burden is basically the load that is connected to the VT or the potential transformer, and that is the voltmeter or the protector relay or the watt-hour meter. Accuracy is basically maintaining that percentage error based on mirroring voltage transformers that are used for mirroring and voltage transformers that are used for protector relay. There's a different accuracy class that has to be maintained, and you'll see that on the nameplate. Next is the thermal rating, right? Okay, so as we connect the burden, there's a thermal rating that has to be maintained. Next is total weight, right? And in this case, basically we don't have oil, but we have basically cast resin or epoxy. Let's see. Oil comes into play when you have voltages above 34.5 kV, or maybe around that 34.5 kV and above, when you have to utilize high voltage inductive transformers, where basically you have oil. The winding is immersed in oil. But on the medium voltage applications, most often it's cast resin or epoxy resin. That is okay. So basically, like I indicated, we have a type, right? So this is the type. So 72.5, right? So that tells you that the nominal voltage is 69 kV, and the maximum is 72 kV. Okay, so like you are saying that this is a though I made mention that it's mostly used for medium voltage applications. Sometimes it extends to 69 kV voltage applications in switchgears. So it let me rephrase this. It starts from 69 kV, 34.5 kV, 13.8 kV, 6.9 kV, 4.16 kV, and 2.4 kV. That is okay. So the maximum system voltage is 72.5 kV, right? And the nominal is 69. And the power frequency, like I indicated, those are over voltage conditions. Okay, so this one is 2 times 72.5. Okay, volts. So that's how they achieve or 69 times 2, which is about 138 kilovolts. Next is the BIL, due to switching and lightning impulse. So that is the installation that can withstand all those higher voltage. And for power frequency, I explained to you the conditions or the phenomena that can occur in the power system network that can result in a power frequency over voltage. The first one is what? Fault recovery from the phase to earth fault clear, load rejection, ferroresonance condition, and sometimes Ferranti effect. Ferranti effect is basically when you have a lightly loaded long line, right? And due to the capacitance, capacitive effect of the line, it could be cable. Cable has a lot of insulation, so capacitance, right? Could be a transmission line, right? Long line. And the straight capacitance can cause over voltage condition on the end of the line, and especially when it is unloaded or lightly loaded. Next is the rated frequency, right? Either 60 Hz and over voltage factor. So it means that this is how much over voltage it will go. So this is the voltage rating factor, right, for 1 minute. Okay, so the primary voltage is 69 kV, right, line to line, and 40.25 kV line to neutral. Okay, the serial number, the year of manufacturing. Then let's take a look at the circuit on the primary side. Okay, so H1, H2, right? So polarity comes in. As you can see, this is the polarity, right? Okay, and this one is the ground, the top. On the low voltage side, you can see this is the polarity, right? So this one is a 2-core, right? It has 2 core, right? The X and the Y, right? So X1, X2, X3, Y1, Y2, Y3. Okay, so within the PT or the VTs, you see the different set of cores, and one is each one is dedicated for a different function. Okay, so X1 minus X3. Okay, so it's saying that between X1 and X3 we have 115 volts. Yes, and between X2 to X3 is 67. So that is line to neutral. All right. So for line to line, X1 to X3 will give us that voltage. Then for line to neutral, X2 to X3 will give us that voltage that we need. Okay. Then Y1 to Y3, right? We can achieve a line to line voltage of 115 volts. Then Y2 to Y3, we can achieve that 67 volts. Now let's talk about the ratio, right? Okay, so it's telling us that between X1 to X3, the voltage ratio is 350, and between X2 to X3, the voltage ratio is 600:1. Similarly, for the second core, which is the Y core, the ratio between a Y1 to Y3 is 350. That gives us, the secondary terminal voltage of 115. Then the turns ratio between Y2 to Y3 is 600:1. Now let's talk about accuracy in the bearing, right? Okay, so ZZ is basically tells us different bearing. We have a different bearing, bearing ZZ, XX, and YY. So they all have a different typical bearings based on this notation, right? I think ZZ probably about 50 VA or so. Okay, so point 3 is your accuracy class. So what it's trying to say is that it should maintain less than 0.3% error and reproduce faithfully. 0.3 or less, and reproduce faithfully the secondary voltage based on the primary voltage without any deviation. Similarly, this is the accuracy class shown over here. Next is the thermal burden, right? Okay, so thermal burden is basically when you go over in operating during emergency conditions, it's going to lead to heating, etc. So that is how much thermal burden rating that we should exceed. Okay, and applicable standard in manufacturing, in designing in manufacturing. So IEEE C57.3 basically tells us the standard that was used in the design and manufacturing of the standard. Next is the total weight. Okay, so this one is 591 pounds, right? And this one, on the other hand, has oil as an insulating medium. So, like I told you that sometimes you can have an oil as an insulating medium, and sometimes you can have a cast resin or epoxy resin as an insulating medium. In that case, you don't need oil. Lastly is the last bit, basically. So after watching my presentation, right? Okay, if you like my presentation, don't forget to subscribe to my YouTube channel. And this is the name of the YouTube channel, Work and Happiness, talking to the engineer. And if you like my presentation, don't forget to select the like button, okay? And share. And re-emphasizing, that there are tons and tons of presentations that are in my YouTube channel. And as a young engineer, starting your career as a developing engineer, as a mid-career engineer, as an experienced engineer, as a consulting engineer, many disciplines of engineering. So there are tons and tons of presentations out there that will help you to refresh yourself, to learn and develop yourself as an engineer. With that, I'll say thank you so much for your listening ears and look out for the next presentation. Thank you.